Okay, folks, the last idea that we're going to do in this lesson is we're going to think about what happens when we add up not just finitely many terms in a geometric series, but add up infinitely many. And that might seem a little bit crazy. It might seem impossible. How can you add infinitely many things together? Believe me, this is a well-studied and understood part of mathematics, but it does deal with this kind of interesting, tricky notion of infinity. And to treat that really rigorously and properly, you'll need to go on in mathematics. You'll see a lot of this if you go on to calculus. For now, we're not going to get into the very rigorous details. We're just going to start with a sort of intuitive example and then generalize that to a formula. Let's go ahead and look at it. Let's consider the geometric sequence 1, 1/2, 1/4, 1/8, 1/16, etc. Let me see. Okay. So first of all, is this a geometric sequence? I claim that it is, and I claim that you can tell by looking, each time we move from one term to the next, we multiply by a half. And that says to me that our r is a 1/2, and we also have a1 that's equal to 1. And what I'd like to do is, so that tells us the initial term and the common ratio, and what I want to do is try adding up some of the terms. So if we want to write down a formula for the terms, it would look like, so this is a formula for an. This is just a formula for the nth term. It doesn't tell us something about what we get when we add all those terms up. But formula for an is equal to the first term, 1, times r, which is 1/2, to the power n minus 1. So an is equal to, I'll leave it like this, 1/2 to the n minus 1. Okay. Let's look at what we call partial sums. Partial sums is when we want to look at what happens when you add up infinitely many, but let's just try adding up just a few. And remember, the number we use to refer to how many terms we add up is k. So when k equals 1, we just have the first sum, it's just 1. When k equals 2, it's 1 plus a half. K equals 3, it's 1 plus a half plus a fourth. And k equals 4, it's 1 plus a half plus a fourth plus an eighth, and etc. ... Now, the sums, well, the first one is just equal to 1. The second one, we need a common denominator. It's going to be 2, and if we add them together, we get 3 halves. And, of course, we can write that as a decimal if we wish. That's a 1.5. This one, we have to do that 1 plus a half plus 1/4. We can figure it out as a fraction. I'm just going to leave it as a decimal. This is 1.75. This one is 1 plus a half plus a fourth plus an eighth. This one is 1.875. And maybe we just do one more of these. This would be k equal to 5. Whoops. When k equals 5, we get 1 plus a half plus a fourth plus an eighth plus a 16th. And that's all equal to 1.9375. Now, these numbers, the partial sums, they keep getting bigger. And that makes sense because we keep adding more and more numbers on. Oh, I made a mistake here. This is 1/16 is the fifth term there. I left off a 1 there. But the amount that we add each time is getting smaller and smaller. It's only half as big as what we added up before. And these numbers, 1, 1.5, 1.75, 1.875, 1.9375, I'm going to pose the following question or observation. I'll call it a question. Are these partial sums, that is to say the numbers we got for our answers there, are they approaching 2? So 2 is my guess. All right. Now, I'm going to, of course, we can't sit with the calculator and actually add up all infinitely many of them, but I'm going to do two things. I'm going to draw a picture for you that hopefully will help to suggest that the answer is, in fact, if we were to add all infinitely many of them up, we would get 2. And the second thing I'll do is I'll translate that picture into a formula. So, are the partial sums approaching 2? I want to look at the number 2 on a number line. And let me see, if this is 0, let's suppose that we have a number line of length 2. And let's imagine we start here at 0. And we walk half of the distance to 2. So walk halfway to 2. So that means we walk from 0 up to 1. And what is the distance that we walked? It's a distance of 1. And the point is that's like the first number in our sum. Okay. Now, we are going to continue walking, but on the next step, we're starting here at 1, and I'm going to do the same strategy, which is to walk half of the remaining distance to 2. From here, we walk halfway to 2, and this distance, well, from 1 to 2 is 1, and this is a half of that, so this is distance of a half. And if you want to think about adding up the sum, the first term 1 plus the second term a half is like where we are now on the number line. On the number line, we've made it to 3 halves, or 1.5. So our first stop was at 1, our next stop was at 1.5. That's where we are now. Now, I'd like to start here in our next step and travel half the remaining distance to 2. It may or may not be clear that this distance right here is a distance of a half, right? Because this was 1, and we took a half of it off there. This is a distance of a half. So if we travel half of that distance, we're only going to travel a quarter. So this guy is going to go 1/4. The total that we get here, I'll put a little dotted line up to the top, that total is 1.75 that we've traveled from the very beginning. From here, on our next step, we're going to travel half of the remaining distance, and that half of the remaining distance is 1/8. So this is 1/8. The reason was that, let me see, this was a whole, this is a half. Half of that half was a quarter, so there's a quarter left. Half of that quarter is 1/8. The next one is going to be half of the remaining distance to 2, and that'll give us 1/16, and so on. And what you can see is no matter how many times you repeat this step, you never reach the number 2, because each time you're only going half of the remaining distance to 2. So you never reach 2 in any finite number of steps. So observations, it doesn't reach 2. The sum, that's what we're looking at. The sum doesn't reach 2 for any finite k. But if we look at how far away from 2 we are, the distance away from 2 is getting smaller and smaller and smaller. So 1.75, this one was a 1.875. The next one was, oh, here, let me do this in green, 1.875, and then 1.9375. We're going to keep getting closer and closer to 2. This distance keeps getting smaller and smaller and smaller. So even though we don't reach 2 in any finite number of steps, we get, the way that we like to say this in math is we get arbitrarily close to 2. So we get arbitrarily close to 2. Now, let us translate this into a formula. I think that when we add up all infinitely many of these things, I think that the answer should be equal to 2. That's my conclusion. So let's go ahead and see if we can make a justification for that answer using the formulas that we had before. So recall we have the formula, the sum I equal 1 to k of ai is equal to a1 times, and the formula goes 1 minus r to the k over 1 minus r. And in this particular sequence, we know what the various values here are. A1 is equal to, well, we said before, we calculated A1 is 1. So A1 is equal to 1. And then this is going to be 1 minus 1/2 to the k over 1 minus 1/2. Okay, and this represents the sum of the first k many terms for any number k. You can imagine plugging a number k in here, like the number 3. Then I just am curious to focus on just the numerator of this fraction. It's 1 minus something. And as k gets bigger and bigger, we're raising 1/2 to a higher and higher power, which means that this term, 1/2 to the k, is getting smaller and smaller, closer and closer to 0. And as k goes off towards infinity, as k, let me write it like this, goes towards infinity, 1/2 to the k goes towards 0. So if we imagine in this fraction, if you imagine k equaling infinity, we can't actually let k equal infinity, because infinity is not a number, right? It's just this concept, something bigger than all the numbers. But we say something like, as k goes to infinity, instead of saying it's equal to, we say as it goes towards, 1/2 k goes towards 0. And that means that when we look at this sum, I equal 1 to infinity, as k goes towards infinity of ai, what is it going to be? Well, the rest of the fraction stays the same, 1 times, and on the bottom is still 1 minus 1/2. And as we go towards infinity, it's 1 minus, and that 1/2 to the k becomes 0. So this is just what we get, substituting in this value for k here, and this value for 1/2 to the k here. Okay. So how do we make this proper? How do we actually add up infinitely many things? That is the whole theory of series, infinite series, and that's made more rigorous in calculus and still more rigorous in real analysis. We're not going to worry about that too much now, just the intuitive notion. What we've now got is an expression that doesn't have any variables in it. We should be able to figure out what this is equal to. The number in front is 1. Top of the fraction, 1 minus 0 is 1. Bottom of the fraction, 1 minus 1/2 is 1/2. The 1 in front doesn't do anything. The 1 on top, we leave there. The 1/2 we bring to the top and we flip it. So this is all equal to 1 times. If we flip that fraction, it's 2 over 1, which is all equal to 2. So we've gotten that this infinite sum, if we add up all infinitely many of them, is equal to 2. That's the basic idea. That's how we sum this series, this infinite series. The next thing we want to do is just translate that into a proper formula. And the key thing to notice, let's write it down. This is the sum of an infinite series, geometric series. So suppose that we have this an is a geometric. So an, the terms are given by a1 times r to the n minus 1. And then this is only going to work if, when you look at the terms, if they keep getting smaller and smaller. That's the only way. If the terms keep getting bigger and you add all of them up, you're just going to get infinity in the end. So this kind of thing only makes sense when that r is not going to cause things to get bigger and bigger. In particular, we want r to be between -1 and 1. So -1 less than r less than 1. Okay, those are the assumptions that we make. Then, what this says is that we can, notice, maybe this is important, a1, the first term, can be anything you like. It's just that the common ratio, the thing you multiply by, has to be size less than 1, greater than negative 1. So, this sum, the sum I equal 1 to n of an is given by the following. A1 times, it's still a fraction, the bottom is still 1 minus r, but on the top, instead of 1 minus r to the k, we think of that r to the k as going to 0, just like it did up above. That was like the 1/2 to the k above. So the only thing left on the top is 1. So it's a1 times 1 over 1 minus r. And this is our formula for adding up all infinitely many elements in a geometric sequence. Okay. That's it for now. We're going to go ahead and use this formula in the next video to actually calculate some more. We've calculated one geometric sequence. The sum of the sequence 1/2 to the n is equal to 2. And now we're going to look at some more infinite sequences in our next video.